Thank you, Francisco. Can you still hear me okay?
Perfectly.
Thank you. All right. First of all, good morning, Australia, New Zealand. It's really a pleasure to be talking to you today. First of all, I have to apologize for my last two sessions. My first one, I had an accident on the way to come home to do this one, and then I couldn't do it. I couldn't and also didn't have time to alert anybody else about it. I really apologize for that one. The second one was a confusion about the dates, and I just did not know about the dates, and that's the reason why. But finally, the third one, I definitely wanted to make sure that I'm going to be there, and I apologize for the previous two if you came and waited and just didn't hear me on this one. So let's talk about today big data for Oracle professionals. Little bit about myself before we go. I have been an Oracle DBA architect for about 20 years, or more than 20 years, and that's what is my bread and butter for all these years. In the last 5 years or so, I started exploring big data. And I'll explain to you why that's important and why you should know about it in the first place. But because I explored from an Oracle perspective to the big data perspective, at that time, there was a lot of confusing things about big data, what it exactly it is. I picked up books, I picked up articles, but they were very difficult for me to understand exactly what it was. So I'm not exactly a very smart person. So somebody has to dumb it down for me to understand it. And if I can understand, I'm pretty sure everybody else can understand. So the way I understood it, I'm going to explain to you. And I hope you appreciate that. And because I am from an Oracle background, and I'm assuming most of you are probably, and then I'm just going to give a slant or comparison with Oracle or what you should do to make a transition, etc. Because that's what a transition I made. So first of all, let's go to the thinking. Why exactly is this important? What do you have to know? If you're already established in the Oracle space, you're probably very well versed in why is that. The way it works is that over the period of time, from this point on to that, the traditional databases, including Oracle, the relational databases, they are probably going to go like this. After some time, they're going to probably flatten out and not grow up anymore. And there will be some organic growth, like a $1 billion company may become $2 billion company, and it might just increase some more database size. But that's not a growth in terms of usage part of it. It'll be an organic growth. Whereas in comparison, if you see, the big data didn't really take off for about last 10 years or so, but after that it's picked up really big, and I think it's going to go significantly high. Why? Because the use cases are so different, and that's the reason why it's going up. So in terms of career opportunity, in terms of exciting projects going ahead, or just satisfactory work, if you want to be, big data is the place to be. And that's the reason why I made the transition, and I'm pretty sure you want to be as well. And let's see how difficult or how easy it is to understand it. So let's see the first one here. So again, I explained to you earlier, nobody explained to me very clearly what big data was and why it's important, etc., not in some clear manner. And they often say that if you can explain something to your mother, and you can probably understand it very well. So that's what I'm trying to do here. I tried to do, explain to my mother. Of course, I wasn't successful, but at least in the process, I made my own understanding clear. So let's see what big data is, and we'll go start from this one. Long because you might have heard the terms like this: Hadoop, MapReduce, Yarn, NoSQL, Spark, Flume, etc. And there are terms galore, but I'm pretty sure you didn't have a clear, concise definition or explanation of all these things. So that's my objective today. You see that. Long time ago, there was a company called Yahoo. Those of you go back a long time ago, before the word Google even appeared, Yahoo used to be the search engine of the internet. Yeah. And the difference between Yahoo and Google was Yahoo actually categorized them into this categories. It's like a phone book. So they had category, for example, automobile services. Within that, you have body shops or repair shops or something like that. So there are categories under that. There are actually people who categorize every web page on the Yahoo site. So if you want to look for something, you can go to a category and find out everything about it. So how did Yahoo make money? They made the money by using how many people clicked on that listing. As a result of that, Yahoo got the money. But the question is, how did Yahoo know how many people clicked on the link? That was actually possible from something called a website logs. This is one example of a website log. This very cryptic, something very similar to our Oracle CRS log or listener log kind of thing, but very cryptic. But this is how Yahoo identified from this IP address, people clicked on this link, and as a result of that, so many links happen, and the link owner should pay some money, etc. This is how they monetized everything. So what's the problem? The problem is that these things are really huge. And in terms of not just one source file, there are multiple files. So we're talking about not just that at that time gigabyte was a pretty big thing. So it's several hundred gigabytes worth of data to be analyzed constantly on this one. And actually, in today's world, it will be more like petabytes because of the amount of information being generated. So this information is not that, it's an unpredictable format. There is no prediction of exactly what's going to, exactly who's going to click on that, what kind of format will come in. There will be a new version of some web server, and that will introduce new formatting thing without any explanation, and that's going to be a problem. And similarly, there will be a image, website, sound, or text link, or pictures, etc. There will be all kinds of things, and it will be kind of impossible to predict in advance exactly what those things will be. And the last one is probably even more important, transient. If you don't analyze something very quickly, it's gone. It'll be overwritten by next one and next one and all that. So you have to catch up very quickly. If you don't catch up, you can never catch up with that all, because this amount of things being generated is much, much more compared to how much is consumed. Then you will never catch up and never be able to do something. So it's important to have this thing. Years later, another company came in. You must have heard of the company called Google. They did the same thing. Only difference is that Google allow you to search something. When you do a search something, let's say you're searching for Australian Great Barrier Reef. Suppose you want to searching for that one. You would get a bunch of links on Google site. How did Google know all that thing? What Google does is that it goes to every website, all possible websites, and extracts information from those websites and puts into its own repository, metadata repository. So when you go and search in Google, it does a searching in its own repository, and then if you click on that, it will goes to actual website. That's the reason why sometimes you might have seen that if you find something in Google, but you click on it, it says the link doesn't exist. That's because the repository wasn't updated after the link, the website disappeared. Other thing. Anyway, the point is that Google had to do the same thing as well, but they had the exact same problem. Too much information. In fact, actually, it's more information that Yahoo had, because now they are going to talk about all the websites in the entire world, and all kinds of web pages, all kinds of content in the web page, like text, sound, video, or all kinds of things from there, and extract and put into a repository which can be searchable. That becomes extremely difficult as well. So we think about that. The problem is that volume. No doubt about it. It's not just a few hundred gigs here and there. We're talking about a few hundred petabytes, and not just here and there. They're constantly being generated and constantly has to be consumed. That one. And the variety part of it, we just don't know exactly what's going to come in. It's going to come in as a link. Is it a text? Is it some kind of a document, like a doc file, some kind of a format that will be totally different? Is it marked up? Is not marked up? Sound, video, unformatted text, all kinds of things. There is no way to predict in advance exactly what kind of content is going to come in and do that. And velocity, and things are coming in at a constant pace, in such a rapid pace that unless you consumed it, it becomes impossible to just catch it up afterwards. There's no point doing an analysis after it's already passed by. So you can't really do that. Velocity is also important. These three, volume, variety, and velocity, these three V's are often called the three V's of big data. And this is the problem big data is going to solve. Of course, the word big in big data is relative. What is big is definitely relative. But what is generally assumed that these three V's constitute what is a problem in big data. So let's see how we solve it. And big question is that why can't we solve it in a typical relational database technology, like Oracle, MySQL, SQL Server, and all that thing? Why can't we use it? Why do we have to go and think about an entirely different technology to address this problem? Well, let's see what the problem is that. So in a typical Oracle world, what do? Let's say you want to you're deciding an application. Let's say a particular application called customers thing, and you have a simple table called customer table, cost ID, name, and address. It's very simple. That's a typical design you do in a relational atmosphere, the customer thing, because you're expecting a customer ID to come in, expecting a name to come in, an address to come in, and you create this table. Your developers create applications on the top of it, and everything is good. Suddenly, you discover one problem, that people want to add spouse to it. What do? Well, it's not a serious problem, but you say alter table add spouse. The problem is that if you do alter table add spouse, all your programs have written on that, they have to address this new column. Hopefully, your programmers are a little bit okay. They didn't do a select star sort of thing. They actually select the column names. In that case, the new column will not create a huge problem, and that's not a huge problem. But you can't assume that. They may not have done that. So you have to do something called impact analysis and all thing. Until the impact analysis is complete, you can't add it. And in between, if your people are coming in, the spouse information is coming in, you can't really consume it. You have to throw it away. That's a serious problem. But it's not that much a problem. You can still do it. But suddenly you discover a new problem. People may have multiple spouses. People get married, then they get divorced, they marry again. In some cultures, you can marry multiple people and all that. So now suddenly you designed something that's not going to work because it's the spouse thing. So what do you do in this case? By relation technology, you say, oops, mistake. Let's create a separate table for spouse, call it child table. Spouse, custody name. Custody is the one that is a foreign key to the parent key custody in the customer table. And you have a name, spouse name there, and a column called current. So in that case, you continue to keep on the spouse names there, and this is the thing. Great. This is a solution, of course, for that relational solution. Great. The problem is that until you complete this table separation and create this table, you have to stop your application, and your application cannot do anything until this separation is complete. And with the impact analysis, everything else, that might take ages to complete. In between, if the spouses are coming in, you have to stop consuming that information. That's a huge problem. Then keep on doing it. Then suddenly say somebody says, let's add the employer information as well. But now this time you got a little bit smart. He said, I don't want to do that. Let's create a separate table called employers table, cost ID, and there's a foreign key, etc., so that you can continue that. But until you create the table, your application cannot do anything. You simply have to wait. See the problem here? The problem is that it requires you to change the database before you can consume or work on any information that comes in. Now, that's a fundamental problem in a relational technology, which is fine if you know in advance all those things, if you know exactly what's going to come in. But if you do not know exactly what is going to come in, this will fail. That variety part of the big data problem is exactly going to hit in the head on the relational world. So this doesn't work. So how exactly will it work then? To make it work, let's think about how do we human beings think and process information? Do we go and create tables in a mind? Hardly. So what do? Let's say you do this way. What do, you say this way, say name equal to data. You think in this terms. You have something called name equals certain data, relationship equal to data, and all the things. Sometimes it could be different. For example, married to and or relationship with. That might be mutually exclusive, or maybe not, but hopefully it is mutually exclusive. And if you're some friends, for example, you have multiple data points, you may have to repeat all those things. So this is something you think in process in your mind. How do you store it? You store this way. You say you talk to somebody. You say, hey, what's your name? First name. Our first name is John. Then John is a spouse name. John's name is Jane. So in your mind, you're constructing this little snippet of information. First name equal to John. Then when the John keeps talking, hey, my wife, so and so. So you say John's spouse equal to Jane. And then say, okay, my child's name is Jill. And Jill goes to Acme School, and so on. So when you get this snippets of information, you keep on constructing all these things. You have no preconceived idea of a first name, last name, spouse name, child name, or column name, etc. like that. All you have is an empty placeholder on the left side, let's call that the key, the data elements what you want to capture. On the right side, the green color ones are the ones you have the data that actually being captured. So you keep on constructing this as you keep on getting information. And so let's say after some time, you meet somebody called Martha as a first name. So you get the thing, first name equal to Martha. Martha's child goes to Acme school. I said, Acme school, wait a second. What did I? So you rack your brain to find out what did you hear the word Acme school before? Suddenly you realize that, oh, Acme school. Oh, okay, so this is Acme school. And then you suddenly make a connection that, hey, you heard about Acme school from your previous discussion, and that Acme school is this Acme school. So from this, you make an association that Martha's child goes to the same school as Jill, who is John's child. So there are two things. And now you make this connection. You create the new data points by simply talking. We don't create a child foreign key relationship at all. We simply build a relationship between multiple data elements. So you can say Martha go to Acme school, and Martha says the teacher's name is Mrs. Gillen. Now this is a new information you got from Martha. So you immediately assume, because her daughter goes to the same school as Jill goes to, so the teacher's name must be Mrs. Gillen as well. So you mention Jill's teacher must be Mrs. Gillen. So that's fine. That information is not something you got from somebody. That information you got, you constructed yourself. You created a new information based on the information you had before. This kind of goes on like this way. So next, when you met to Jill, you just say, hey, Jill, yeah, I know the teacher's name. Jill says, no, her name is Mrs. Fullmeister. Just make an update in your mind. That means that's done. But Martha's child goes to school. The teacher's name is no longer whatever the name was given before. Now it is Mr. Fullmeister. That's something you keep in your mind. And that's a new information you updated in your mind by these little things in that. So let's understand how you get the information. You have nothing more than placeholders. On the left side placeholder, which is the blue one, you have what kind of data you're describing it. It's an empty placeholder. You just put it there and you associate with the data actually comes in. So first name equal to Irene on the right side. That's the green color one, etc. Irene's boyfriend is Henry. Henry worked for Starwood, etc. Hobby equal to photography. Ex-spouse name is Jane. You say, what did I hear the Jane information? Is it you get another bunch of information you have in your mind. This Jane and this Jane are connected together. Suddenly you are creating intelligence from multiple data. So you are talking about something, you got information in snippets, in bits and pieces, but you didn't have to have them a proper storage mechanism in your mind before you got them. You constructed the mechanism as you got the information, and you kept on building data elements, and you combined multiple data elements to create intelligence. That's how we human beings work all the time. We don't have a preconceived table structure in our mind, because if we had, then we wouldn't be able to process anything. Let's say we don't know the table structure called spouse. Well, if a spouse information comes in, our mind would have shut down. I don't know how to process it. I want to throw it out. Invalid column name or something like that will come in, or unable to insert records and thing. We don't work that way. Our mind can't capture anything and process it. How does it capture? It captures this way. So if you think about this one captures the anything that's on the left side that defines what the data is, and on the right side is what the actual data is. This is called a key, what the data is, and the data itself is called value. That's why it's called a key value pair. This is how we human beings think, and this is exactly how big data solves the problem with a variety of data. It doesn't create this relational tables to put everything in place, everything in a structured format. All it does, it simply creates the key value pair. So as information comes in, it simply puts information on the key side, what kind of information, and puts what information came in on the value side, the key value pair. That's how the first problem with this information called the big data's variety problem. So let's say this is you keep on you're walking, you're talking to somebody, and you heard the story. John Smith and his wife Jane, along with their daughter Jill, were strolling on the beach when they heard a crash. John ran towards. When you are reading the story in your mind, you are constructing these little things you capture from there. John, wife, Jane, daughter, Jill, all those things in your mind, you put that together into a key value pair. And as you keep on reading it, you are constructing this key value pair again and again, again, again. And you can go and capture the key value pair as needed. This is called data intelligence. So this is something that happens in the big data as well. So how does actually big data then work? So this is how the conceptually it works. How does it actually process the information? And then why can't we do the same thing on a relational table? Actually, if you think about it, in a relational world, if you put into a purely relational world, it will appear like you have a table with exactly two columns, the key and the value. That's it. And the key will be a character field, and the value will be a blob, because you don't know exactly what information is going in there. So it could be a text, it could be a sound, it could be a video, it could be anything in that. So you don't know that or a picture. So it has to be a blob. So whatever comes in, you define what the data is. You put in the first column called the key, and the other column called value will be blob. You just put it there. So that will be the thing. Then, if that is the case, why can't we do it? Well, the problem is that if you do it, it will be super expensive. We just don't need to do that. Why super expensive? Well, we'll come to that one. So next one, we say, why is the problem with the big data thing? Is this way. You have a huge data set coming in. Suppose you're trying to find out how many people liked my Facebook post. So Facebook gives you a data file containing all the information about likes and dislikes, etc. Actually, I don't think there's a dislike option, but let's say no comments option, something like that. It says it comes out. So you have this data. You are going to count how many likes and dislikes you have. Well, how do you do it? Well, in a typical computer parlance, which is the way you take it, you go through it one by one. Well, think about it. Let's say you have a book, and you're trying to find out how many times Australia appears in the book. What do? You have to read it. Every time Australia comes in, you have to tick it off. You have a count somewhere, right? But let's say you have 10 friends with you. So what you can do is that you can tear out the book into 10 different parts and give each part to a friend. So you can work in parallel, all 10 of you, all 10 of them, and then they can give the information back to you eventually, and you can simply count them. You can just add them up from every one of them. So that will be much faster compared to us doing it all by yourself. So you're making parallel processing. So, well, but that's not a new thing. The problem is that the difference is that you can't know exactly at any point in time what is the count, because you have to wait until a count comes from everybody. Now that's okay for a Facebook likes or something. That's not okay if you want to count how much balance you have in a bank account, because that something has to be exact and a specific moment in time. So if you can afford to have a little bit of latency on how much it can come in, how much is counting, you can divide the workload. So what happens in the big data world is that the data set comes in, you divide that into multiple worker or computers called nodes. So each node gets a chunk of data. So the main data set is divided into 3 different parts called sub data sets, and then each sub data set goes into the nodes. So this process of dividing the work that comes out and then going across multiple nodes is called map. Then after that, let's say you have a simple program called counter program. All you do in this case is that, by the way, this is pseudocode. Don't think about it as it's not a language or something. It's just a pseudocode. And the pseudocode simply says that while the remaining post, extract the status of like for the specific post. If it is like, then increment the count of like, and so on. So it's a very, very simple program. So what you do is that you run this counter program on each of the nodes. The sub data sets you got, the 1/3 of the entire data set each node got. So that counter program works on this sub data set, and each of them goes separately. And this process, at the end of it, it produces the output file. So for example, node 1 says I got 100 likes, no comments, 300. This one got 50 and 350, and so on and so forth. At the end of it, you combine it together to say add it up, 100 plus 50 plus 150, that is 300, and no comments equal to 300 plus 350 and 250, that comes out to be 900. Very simple thing. So this is how you just have just like you could have added up everything you got from your friends, this computer adds stuff as well. This process is called reduce. So they go hand in hand. So map, dividing the work across multiple nodes in a system, and that's called map. And collecting all the work together to get the final result is called reduce. These two terms, map and reduce, are often called together, and they are usually called map reduce. So once again, what is map reduce? Map is simply dividing the work among different nodes, and reduce is simply collecting the results together to get the final answer. So map reduce. So you understand that word. That's not that complex anymore, is it? So this is saying how the thing. Divide the workload, submit the jobs, and if a job fails, you have to restart in another node and all that. Just like let's say you're trying to find out how many times Australia appears in a book. You have three friends, you divide the work, you tear up the work across all your three friends and they're counting it. And suddenly somebody says, hey, I have to go. I'm sorry, I can't stay. I can't finish the work. So you have to give that work to somebody else. And it's quite possible your friend number two may have done it already or is about to be done. So the work is not much. So you divide the work. Either you divide the first friend's work who left already, divide it up across between the both of them, or based on the workload of each one of them, you might give it to somebody, only one of them. So this is something that happens in computer as well. There are three nodes. One node dies. Then somebody has to decide how much work is completed in there. The remaining work, how can that be given to only one node, or can that be given to divided again and given to both the nodes? All those things has to be decided by somebody. So this is something somebody has to decide that, and so you probably have to write the program to constantly check on the nodes, whether they're dead, the job is running, and all that thing. If the day are died, how do we transit over all the things? You probably have to do all that. Well, if you don't have to do all that, it'll be great, isn't it? Because then you don't have to think about all the mundane details. Well, that's exactly what another system does. A technology exists, which is like a framework, which monitors every node, monitors jobs, finds out the jobs are running or not. If the jobs are not running, what is the reason they're not running? If the job node has failed, can that job be moved to a different node or divided across nodes, and which node has to move to? All that information, that system can determine all that is written for you. And that system is called Hadoop. So what is Hadoop again? Hadoop actually doesn't know what the job is doing and all that thing. All it knows, there are X number of nodes in the system. One of them, is every node functioning how it's supposed to function. If it is not, then can I move it across something? Can workload be balanced across all the nodes and all thing? That's what Hadoop does, and that's what the best part of Hadoop is. So that's what now you understand what Hadoop is. This one. This is the thing. But here's the two things. One is called resource management. You're trying to find out which node has how many resources, how much CPU, how much of memory, how much of IO, and all the thing. You're trying to balance all those things. The other part is applications. In this case, we're talking about applications that runs. Okay, application A runs. How do you make sure that the application can be divided across all those things? Getting Facebook likes is very simple. You divide the work, the file that comes in across all of them. This might be simpler. What if there's something more complex application? In a real world, of course, is more complex. In the past, in the map reduce functionality, the resource management and applications were together, combined all the time. And people thought, well, not necessarily all the time. It's not a good idea to have all the time. The resource management is totally different from applications. So MapReduce, people wrote at Google who brought out MapReduce, they thought more, and they created another one called Yarn, yet another resource negotiator. So Yarn is sometimes called MapReduce 2.0, I think, or version 2. All it does is that it removes the application part completely from the ecosystem and only resource management. So you can define an application as you think and not worry about anything else. So that's called Yarn. So Yarn, very simply put, is nothing but the next generation of MapReduce. That's it. So the concepts are still there. Only what those jobs do, that's not necessary anymore. That's Yarn. Okay, let's go back to the first one again. So you got the subdata sets going to each node. The counter program runs on each node, another thing. But question is that I mentioned to you earlier is that when node 1 dies, so Hadoop makes sure that that workload completed so far by node 1 doesn't have to be redone, and whatever is not completed has to be given to another surviving node, all of things. But the question is that how does the surviving node even get the data? Because remember that the subdata set 1 over here, and which is not visible to node 2 and node 3. So then how does it do it? Well, one option is to make a clustered file system, but that will be very complex, time consuming, expensive, and of course performance inducing. So it's not a good idea at all. So instead of doing that, what Hadoop does is something pretty neat. So let's say one block comes over here. Hadoop reads by block by block. A typical block is 1 MB in anybody, but it could be anything you define, but typically it's 1 MB. 1 MB comes in and it puts into a local file system over here. So I just make copy as a red color copy. But when it does that, Hadoop also copies over a copy of that block to another node, local file system, and another node, another local file system. Remember, this is a local file system, not a clustered file system. So this is like your typical Unix box or Linux box, and you have U01 or user file system or whatever it is. You can just put it there in the file system, and this thing, Hadoop, takes care of that one. And same thing here. Similarly, block number 2 comes from, say, from data set number 2 from node 2, but a copy is created on node 1 and node 3. Similarly, node 3 reads a block from his own data set, creates a copy, block on the node his own local file system, and copies over to the other 2. By doing so, every block has 2 redundant copies as well. So this way, so if the one node dies for some reason, that data is not lost because you have 2 more copies of data on at least node 2 and node 3. This thing is done automatically for you, and it is called a Hadoop Distributed File System, HDFS. Remember one thing, HDFS is not a clustered file system. Big difference is that in a clustered file system, every node can see everything in one place only. HDFS simply moves copies of one to another node, and that's how it maintains that reliability or the redundancy. So that's why HDFS is not called a clustered file system, it's called a distributed file system, HDFS. So that's a big difference. So what is the advantage of that? Well, if you look at the comparison with Oracle RAC, seeing how the thing, this is how Hadoop looks like. So it's not a shared storage. Oracle RAC, as you know, every node, there are 3 nodes in the Oracle RAC cluster. Every node has to see the exact same file system. You have a clustered storage, either you have a clustered file system like a Veritas or something, or you got to have a clustered file system or an ASM volume which is visible to across all 3. They're not 3 different copies. They're just a one copy are visible to across all the 3 nodes. Very, very different thing in Oracle RAC. Data is discrete. So in this case, we just have only 2 copies. What if you had 4 nodes? If you have only 2 copies, that means node number 4 will not have a copy of block number 1 from this thing, right? Because it's only 2 copies over here. So data is not same across all the nodes. So if I go visit this node, it might have a different set of data compared to this node over here. Data is discrete. That's in Oracle RAC, that's not the case. Oracle RAC is exactly the same, regardless of where you go, you will see the exact same data everywhere. Data is discrete. Version control is not required. That's a very, very important thing. If you modify a block on node 1, it is quite possible node 2 has not got that updated copy yet. Or even worse, if the update happens one more time on node 1, it is quite possible node 2 has a different version than node 3. So you can't rely on what you look at the node and if the version control is there or not. Now, is that a good thing? Depends. Depends on the application. Again, as I told you, if it is a banking application, may not be a good idea to do because you must have exactly the same. But if you have a Facebook likes, who cares? Just 1 million likes and 1,010,000 likes. Not going to be different. So this is a big difference about big data systems like on the other systems as well. Concurrency is not required. In this case, I can go to node 1, update block number 1, or at the same time, somebody could go on node 2, update the copy of node 2, block number 2 here. Block number 1 here, copy of it. That's quite possible. Now, In Oracle RAC, that's not even possible, because if it doesn't matter which node you go to. If you want to update a row, that row, if somebody has done the update, you have to wait until the other session commits or rolls back, because it's a locking contention. Concurrency is guaranteed in Oracle or other databases you have. Now, this is not in this big data scenario. That's not guaranteed at all, because there is no way for this to know if another node has a copy of it. I mean, it knows that copy of it. There's no way for it to know if another node is being updated on the same copy or not. That's not something that's not going to work. That's why concurrency is not required on this one. And transactional integrity across nodes also not required. Something Oracle RAC kind of guarantees that. So if you think about all that thing, wait a second, this is not even good at all. It could give me a bad result or a wrong result. Absolutely, this is a wrong result. But think about it. Do you absolutely must have the right results all the time? Like, do you have to know 1,121 likes in Facebook? Or is 1 million good enough? Most likely, you'll say it's good enough. That's why approximate number is definitely acceptable in many cases. But if approximate number is definitely good in many cases, this reduces the complexity of a complex system like a clustered file system, etc., to such a minimum that the cost becomes significantly less. And that's the big advantage of big data systems. Not only the cost, it also makes it highly scalable, because you can actually create more and more. And that's something we'll see that. So what is the advantage? Because you don't have to have this concurrency control, very difficult and complex locking control across multiple nodes, etc. Your processors, your CPU demand is not going to be very high. So your processors need not be super fast. In fact, most Hadoop clusters are very like pizza boxes, like for typically the 4 or 8 CPU, one use servers, you can just plug it in without a complex. Whereas if you Oracle RAC, if you think about it, you got to have a very expensive, powerful servers, because the locking, latching, etc., are going to kill it unless you have some high capacity CPU. Scalable. You want some more data, more processing power, just add another node. Very simple thing. Storage is by design redundant, because one block has at least two copies on two different systems. Yeah, by the way, you can also create multiple copies by configuration, but generally default is two copies, and this is by design. So you add some more, you want some more space, you just add it, keep on adding it. And storage is redundant by design, so you don't have to go through expensive storage like RAID 1, etc. Not possible, not required at all. There's no reason to do that. So you don't have to go to expensive storage like EMC, VMAX, or something, because that's not necessary at all. Many Hadoop clusters actually don't have any external storage. They simply have just a bunch of disks that are internal disk storage, and that's it, as it is. And that's something you can run a whole cluster. In fact, all of you in the room together, hopefully can be close to each other. You can bring your laptops together and create a Hadoop cluster just like that. As long as you have network connectivity, that's all it is. You don't have to have anything else. But that's our advantage of using. You cannot do that in Oracle RAC or something. This complexity, I'm saying, this reduction in complexity, not just reduction, this amazing reduction in complexity brings the cost down so much that you can store a lot more information, do a lot more processing in this Hadoop cluster by doing so. And this is exactly why this thing is kicking up into super fast speed, because now people are realizing that, hey, they can do certain things they could not have done in the past. So it is scalable. So why it is scalable? Asset properties. You know that in relational database system, that's important. That's a very important thing. But do you need asset properties? Again, I just gave the example of Facebook likes, etc. I don't need asset properties because I don't really care about that. So this reliability, this large overhead in data processing, it comes as a cost. If you can remove all that, that cost is gone, and it can become immensely scalable. This is exactly the reason why relational systems have not been very successful in handling really large amount of data, because the inherent problem is it's like a super fast, super powerful engine. But being a super powerful also, you just can't be flexible enough to quickly adapt to increasing needs. And that's something big data systems can do. because they are flexible enough at the cost of reliability. So think about that in many systems, and you will certainly find there are way too many things. They don't need that kind of super accuracy. Approximate accuracy is good enough in many cases. In that case also. But here is example something thing. So you try. It's almost like trying to find a needle in the haystack. So you try to find what are the things you could generally look at? Website logs. Sometimes you combine that with structured data that you have in your relational systems, SOAP messages, Twitter feeds, Facebook feeds, and those kind of things. And those are if you go through all these things, you'll see they are highly unstructured because there's no structure to it at all, and in very voluminous data, website logs, Twitter messages, all thing, and you're trying to find out. Let's say you're trying to find out how many customers gave a bad rating or ranted on your against your company on Twitter, something like that. That's something you'll find out from this thing. And actually, there are a lot of applications written against Twitter feeds that gives something called sentiment analysis, that they can decide what is the sentiment of the customers or the perception of the customers for that company, etc. But so far we talked about everything. So one of the good things about our relational system was that you didn't have to write a program to something to get data. You just had to know a SQL statement, select something from something, and then that's it. That was a simple thing. Because this data is not structured, it's not put in a structured way, you have to write an application, a program to get data out of it. Now, that's a very simple thing. That's why these are called NoSQL databases. And why NoSQL? Because you can't use SQL against it. It's not structured. It's not organized properly. So you have to write programs to do it. And what kind of programs? Java programs. Not something everybody wants to do that, Java programs. So at some point, people refuse to give it a actually serious thought because not everybody can be Java programmer. If you think about it, SQL actually made data powerful, or people are analysts more powerful because they can use data to do the real work. So they didn't have to know exactly how data is stored. All thing that was kept totally different. So SQL empowered those people to be superior at the jobs because it freed them up from relying on another third party like a program or something to get data before to them. So the problem is that big data went back to this old age where you have to rely on a programmer to go onto that because there's no SQL access. You have to write a Java program to do all those things. There's no SQL databases. So when companies discovered this is not going to work very well, so they created another one. I think, I'm sorry, before I do that, let's do one more thing. The key value pair. This is done this way, key and value. This is called a key value database this way. Sometimes you have a lot of things in a single key, like it's called key and document. For example, in a document, you may have also multiple keys. Example could be, let's say, loan application. A key will be a loan application. Document will be an actual application itself. Inside that may have multiple key value pairs, like first name equal to whatever, last name equal to whatever, date of birth, property, and all those things that we have that. So this is called a document database. Typically, it is written in a JSON format, in this format. So you have a curly brace. You can see that how it is stored here. And this is called a document database. So going back to the previous one here, at the end thing, even though you have to write programs to do this, you couldn't actually empower the people who would use the data. So they needed SQL interface to do this one. Absolutely necessary. That's why most companies introduced SQL interface, and so did the Hadoop organization as well. So they introduced something called Hive. Hive is SQL-like interface. It's not exactly SQL, but it's almost SQL-like interface. And the language you use to actually extract the data is very much SQL-like, and that is called HiveQL or HQL. Sometimes it's called. So here is actually how you create a Hive table. Create table account. This is actually Hive. This is not in HQL syntax. But if you look at it, if you are an Oracle professional, you can see that it looks very similar to an Oracle external table, doesn't it? In fact, Oracle Big Data is actually used this way, exactly same way as an external table. And it's simply see the location, user, Hive, db1 account, etc., stored as text file. This is a Hive thing. So I just want to give an example here to show how similar it is to an actual SQL, or how similar it is to an external table in Oracle. So yeah, Hive table. So by doing so, you actually trying to map what you have stored as unstructured data into some kind of structure like account number, account name, and balance. If you can do that, absolutely possible to do this way. And then people can simply select star from accounts where account number equal to whatever. And then Hadoop will translate that, not actually Hadoop, sorry, Hive will translate that to a map reduce job, go across all the nodes and go across all the data sets I have and get the results out and give the results back to you. That happens here. This is how Hive QL looks like. Select count star from store cells, join household demographics, etc. Whatever. If you look at this one, this looks very similar to our ANSI SQL statement, doesn't it? Whereas actually this follows ANSI SQL statement, very similar to Oracle. By the way, also supports ANSI SQL. So if you are familiar with the join syntax there, this is how it looks very similar as well. This is Hive SQL. So let's say here, map reduce is divide the work and collect the results. So this divide the work and collect the result that needs development in Java, Python, Ruby, etc. But if you're a database professional, you certainly don't want to write a Java program. You may not even know Java program. Python is something good to know, but is it absolutely necessary to know that? Not necessarily. So somebody has to define some kind of a tool or a framework. So this thing can be done in parallel automatically without me worrying about it, how to do that. And that framework is called PIG. PIG is a framework that divides the work and makes sure that the work is kicked off, etc. And to do without you worrying about how to divide the work and etc. And the language is used is called PIG Latin. So it's a scripting language for PIG. So here is I'm going to give a comparison between SQL and PIG Latin. This is SQL. Select category, average of page rank from URLs where page rank is more than 2. So it's like I'm a table called URLs, and I'm trying to find out the categories of where the page rank is more than 0.2 and the counts is more than 1 million, etc. This is how you write in SQL, and this is exactly how you write that in PIG Latin. You can see the syntax is not the same, but it's very similar. You can see that the concept is similar. For example, it's fast filtering, then the grouping, then output for each, etc. So again, I don't worry too much about the syntax. I just want to show you the syntax so to appreciate how it compares to SQL itself. So this is what's called PIG Latin. People still wanted something like a database, which them in their mind, database is something like a table. You have table where you can define the columns, you can define the rows, etc. So that's why Hadoop organization brought out a tool called Hbase. Hbase is a database built on Hadoop. Actually, the Hbase goes back to previous. Before that, it was built by Google called Big Table, and Hbase is built based on the concept of big table. So what Hbase does is that it presents the information stored in these unstructured files into a structured file. That's what Hbase is. In fact, you will find Hbase is being used in many companies. Everything that kind of gives us the semblance of a relational database from an unrelational world. And HiveQL is SQL-like, but not the same query language. And PIG is the procedural logging without the map-reduced code, etc. So Yarn is the map-reduced code in Java. No one likes Java. Well, at least I would say that thing. No one likes to write code in Java or learn a language like Java if you are not a Java programmer. So most database professionals don't want to write this complex, something to learn, you might make mistakes, all that thing. So why do that? So what you want a normal programming language. For example, Python. That's a great programming language to learn. By the way, if you haven't learned that, it's a good thing to learn that. So you want to learn that. So Python, you want someone to translate this thing, Python, into Yarn thing. That will be great, isn't it? So you don't have to know Java. So it's like this way. You are communicating to somebody in Spanish, but you don't know Spanish. So you want to try an interpreter. So you will talk to the interpreter, and he or she will talk to the person in Spanish, get the response back, and give it back to you. So you don't have to know Spanish at all. Similarly here, you won't write in Python, but behind the scene, you want somebody to write the code in Java and give it as a map-reduced code in Yarn. So this is something you like to do. And there is something was available afterwards, and that is called Spark. So Spark takes the normal programming languages, etc., converts into map-reduced code in Java and gives it to Yarn to continue to run it. And by the way, what is Yarn? Yarn is, remember, version 2 of MapReduce. So in this case, we got this one Hadoop processing is in. But what is the big difference between Hadoop and non-Hadoop relational world? Here you can see that Hadoop processing is done in files, not on data sets. So you give it a file, it has to divide the work across multiple nodes, and by the way, each node gets a file and it creates another file, which goes back to you. You compile the results and all the things. So think about it. It's not going to be a real-time interactive environment. It's going to be a batch processing all the time. For those of you who have ever worked before Oracle days, remember COBOL? COBOL used to work this way. You run a COBOL program, you get a data file, you create something. In fact, mainframes work in the same way as well. They're not interactive, they're just job-oriented. You kick off a job and you wait for the job to complete. And you compile the results of multiple jobs into a single output results if you want to have it. Same thing also how Hadoop processing happens in files. It's a very big difference and something you have to keep in mind. It's not real time. However, who cares about files now? Memory has been pretty cheap. When I first started my career, there was no laptop, by the way. It was all desktops, and desktops were my desktop was 4 kilobytes because I was a cheap desktop at the time. And in fact, I remember that the first expensive desktop I got, the memory was 1 megabyte memory, and not even gigabyte, something 1 megabyte. Today, my laptop has 16 gigabytes. So memory and you talk about memory has been pretty cheap. And you're talking about memory in the pizza boxes, those things are even cheaper. So question is, why, if I have so much cheap memory available, why do you have to care about files all the time? I don't need to care about files. So interactive processing also needs faster access. I can't wait for the system to create a file, and then a file has to be put in a file system and read it again from the file system and give me the results back. And can't do that. So if your memory chip, why can't I put in the chip itself? That's why another one comes in called Spark. Spark has something called Spark Core and Spark Cell that allows me to put stuff in memory. So Spark Cell is something is like a cell interactive cell interface to the Spark Core that allows me to do stuff which is not possible to do that. That allows me to create Python programs, allows me to create this data sets in memory and then get back memory and all the thing as well. Spark SQL is another SQL language which does everything that I've done before, which Hive does. The only difference is that it doesn't create files and read from the files. It can create everything in memory and read from the memory for superior access, faster access. It's still not interactive enough like a relational system, but it's so much faster than the typical file system access. It looks almost interactive. And in many applications, that could be good enough. Machine like mlib is a machine learning library. Spark R is if you can write some program in R, Spark R can convert that into MapReduce code in Java, etc. PySpark is another one called the Python interface to Spark. So you can write Python programs. You can use PySpark to create Python programs and so on and so forth. You can use Java, Python, or a new language called Scala, which is very good for big data applications most recently. Remember that divide and conquer is the key here. And I think non-shared division of data is very important. That's a very important thing. Non-shared division of data. That means every node gets their individual data set and they're not shared. Because they are not shared, the machine doesn't have to worry about who got what and who got the what version, concurrency, version control, etc. are not important. And it can be stored in local storage system instead of an expensive SAN system, because you don't need any node 1 doesn't have to know what node 2 has, because it may have a copy or not have a copy. That's not really important. And the copy is there only for one reason: redundancy. It's not there for anything else. So Hadoop is a framework. Hadoop doesn't tell you or doesn't do work for you. Like, for example, you want to count Facebook likes, you have to write the program to count Facebook likes. Or what do you want to do that? But Hadoop simply runs it and make sure that when the node fails, it moves to the other side, and so on and so forth. So you have to write the programs. Big data is batch oriented. Keep that in mind, important enough. It is not interactive, not like every time you are writing a SQL statement, like you can say Spark SQL, for example, right? SQL. Behind the scene, what Spark does is that it divides, that creates a MapReduce job, sends the MapReduce job to all the different nodes, get the results back, compile the results, and get the results back to you. So you don't see all the steps behind the scene, but that's what's happening. Each one is a batch program. The only difference is that it is so fast because of the memory access. It might appear like a batch program, might be an interactive application. It's not. It's actually a batch program, something you have to do it yourself. Hive is SQL-like, but it's not exactly the same thing. It's called Hive SQL. Pig Latin is a 4GL-like scripting language to divide the work across multiple nodes. But again, if you're using Spark and all the thing, you don't have to know Pig Latin at all. So things like that. And Spark, you just memory to make it faster, etc. So at this point, you must be excited. Okay, I want to learn something about it. All right, actually, it's actually very simple. In fact, it's free. The two companies, by the way, I don't work for any of the company. I'm not going to endorse either of the company. The companies are Cloudera and Hortonworks. Both of them provide pre-built virtual machines. You can download that and you can learn that. You can just use, for example, Cloudera has that for one virtual box. If you install that on virtual box on your local laptop, that's good enough. It's not going to be powerful enough to run real jobs, of course, but for learning, absolutely fine. It gives you an idea of how things actually work before you jump into that. And they're totally free. In terms of learning training programs, Cloudera and Hortonworks, both of them, they have some tutorial videos, all thing on the website also. Very good. But it's definitely worth investing in some book or something just to get through that. And hopefully now you got the idea of how things are. It will be a very simple thing to go ahead and actually work on those. And now those books you read will make some sense as opposed to getting lost in the whole terminology jungle here. So, with that said, I thank you. I hope I gave you enough information. I started off with why it is important to begin going to big data bandwagon because of the trend is going up. I think he's got that part very clearly. You also understand now big data is cheaper to operate compared to a relational system, but at the cost of what? At the cost of reliability, consistency, transaction integrity, and all that thing. So, if those things are important, you cannot do that in big data environment. You have to do that in a relational environment. That's why relational is not going to die. It's going to stay forever. However, applications are coming up nowadays. They don't necessarily have to have that integrity constraints, etc. That's perfectly good candidate for big data systems. And that's the reason why I think it's going to go up significantly. That's exactly why you have to go up. I also gave you a bunch of tools and technologies, what they actually do. Hopefully you got that, like for example, things like Spark, etc. Very good. And I also give you a resources where you can learn all those things here. So with that said, I hope you got something out of it. I hope you appreciated the thing, and hope you have more questions than answers at this point to propel you forward.